All right, welcome. Got an operating systems exam coming up? Perfect. You are in exactly the right place. We're going to skip all the fluff and dive right into the core concepts and, yep, the calculations that you're actually going to be tested on. Okay, let's get into it. I mean, just think about it for a second. Your computer has a finite amount of power, a finite amount of memory, and yet it's juggling all of this stuff at once without just, collapsing into a pile of digital dust. How does it do that? It really feels like magic, but it's not. It's the work of one incredibly clever piece of software. And that, of course, is the operating system, or OS. Think of it as the master manager, the traffic cop at a crazy intersection, or the conductor of a huge orchestra. It's this absolutely essential software that sits right between your apps and the physical hardware, making sure everything plays nicely together. So how does it even begin, this incredible juggling act? Well, the very first step is to get all the work organized, and it does that using two really key concepts: processes and threads. You see, every single program you run, your web browser, your music player, even a simple calculator, is known to the OS as a process. I like to think of a process as a chef in a big, busy kitchen. They've got their own recipe, that's the program's code, their own set of ingredients, which is the data, and their own little workspace. And the OS is the head chef, managing all these other chefs in its kitchen. Now, a process isn't just on or off. It actually moves through this whole life cycle, these 5 states. It starts out as new, as it's being created. Then it moves to ready, which basically means it's standing in line, waiting for its turn on the CPU. When the OS finally picks it, it's running. If it needs something, like reading from a file, it goes into a waiting state, stepping aside to let another process run. And then finally, when its job is all done, it's terminated. And the OS is just constantly shuffling processes between these states. It's a huge fundamental part of its job. But what if our chef, our process, could do more than one thing at a time? Well, that's where threads come in. A thread is kind of like an assistant for the chef. So think about your web browser process. It can have one thread fetching images, another thread playing a video, and a third one responding to your mouse clicks, all happening at the same time. We call them lightweight because they share the same kitchen, the same resources as the main process, which makes them way faster to create and manage. Okay, but here's a key distinction for your exam. Not all threads are the same. You've got user-level threads, which are managed entirely by the application itself. They're super fast, but the catch is the OS has no idea they even exist. So if one of those threads gets stuck waiting for something, the whole process just grinds to a halt. On the other hand, you have kernel-level threads. These are managed directly by the OS. Yeah, they're a little bit slower to create, but the OS is totally aware of them. So if one thread has to wait, the OS is smart enough to just schedule another thread from that same process to run instead. It's that classic computer science trade-off, pure speed versus intelligent management. So now we've got all these processes and all these threads lined up. They're all in that ready state, just waiting for their turn. And this brings up a massive question. How in the world does the OS decide which one gets to use the CPU next? This whole decision-making puzzle is called CPU scheduling. And right off the bat, there are 2 main ways to think about this. First is non-preemptive scheduling. It's very polite. Once a process gets the CPU, it keeps it until it's totally finished, or it decides to give it up on its own. It's simple, but a really long process can just hog the whole system. Then there's preemptive scheduling, which is what pretty much all modern systems use. Here, the OS is the boss. It can interrupt a running process at any moment to let a more important one have a turn. It's definitely more complex, but it's the reason your computer feels so responsive. Okay, so let's look at some actual algorithms. The most basic one is first come, first serve. And it's exactly what it sounds like. It's just a simple line. The first process that shows up is the first one to get the CPU. It's non-preemptive, super straightforward, and really easy to implement. All right, let's get our hands dirty with a classic exam-style problem. We've got 5 processes here, P1 to P5. And you'll see 2 really important columns. Arrival time, that's the exact moment each process gets into the ready line. And burst time, that's how much CPU time it needs to finish its job. We're going to run this exact same set of jobs through a few different algorithms and see what happens to the wait times. Using first come, first serve, the math gives us an average waiting time of 3.8 milliseconds. Now, for your exam, you absolutely have to know how we got that number. Let's walk through it. P1 arrives at time 0 and runs immediately, so its wait is 0. It runs for 4 ms. P2 arrives at time 1, but it has to wait until P1 is done at time 4, so P2's wait time is 4 minus 1, which is 3 ms. P3 arrives at time 2, and has to wait for both P1 and P2 to finish at time 7, so its wait is 5 ms. You just do that for every process, add up all those waiting times, divide by 5, and you get 3.8. So that's our baseline. The question is, can we do better?
Let's try a smarter way. Shortest job first. So instead of a dumb queue, the OS now looks at all the processes that are ready to go and picks the one with the smallest burst time to run next. The whole idea is to get the quick jobs out of the way as fast as possible to keep the line short.
And look at that. The average wait time drops all the way down to 3.2 milliseconds. It's not magic, it's just a better strategy. By running the shortest jobs first, the OS clears them out of the queue super quickly. Little jobs like P3 and P4 don't have to wait behind bigger ones anymore. This clears the whole queue faster, and that lowers the average wait for everyone. For the exact same amount of work, we just improved our efficiency by picking a smarter algorithm. But hang on, what about fairness? With shortest job first, a really long process could end up starving if a bunch of short jobs keep showing up. Round Robin is designed to solve that. It's preemptive. Every single process gets a small slice of time on the CPU, something called a time quantum. If it's not done when its time is up, too bad. It gets kicked to the back of the line to wait for its next turn. And here is the big trade-off. Using Round Robin with a time quantum of 4 milliseconds, our average wait time just explodes to 11.75. So what happened? Well, this algorithm cares way more about fairness than it does about raw speed. P1 runs for its 4 milliseconds and finishes, no problem. But look at P5. It needs 5 milliseconds, so it runs for 4 milliseconds, gets interrupted, and then has to go to the very back of the line and wait for everybody else to get a turn before it can run for its last little millisecond. All of that stopping and starting adds a lot of overhead, and it makes the total time everyone spends waiting go way up. The system feels more responsive, but the average wait time gets worse. That is a critical concept to remember. Okay, so we know how the OS manages jobs and decides who gets the CPU. But where do all these processes actually live? That brings us to our final core topic, memory management. First, let's just nail down some key terms you have to know. Our physical RAM is divided into fixed-size chunks called frames. A process's data and code are also broken into chunks. If those chunks are fixed size, we call them pages. If they're different sizes and organized by what they do, like a block of code or a block of data, we call them segments. These are the fundamental building blocks. And now for what might be the OS's greatest magic trick of all, virtual memory. What it does is make every single process think it has this gigantic, private, continuous chunk of memory all to itself. But in reality, the OS is furiously swapping these pages back and forth between the fast, small RAM and the slow, enormous hard disk. It's this illusion that lets us run programs that are way, way bigger than the physical RAM we actually have. So that leads to a really important problem. Let's say your program needs a page of data, but that page is currently sitting on the hard disk. And worse, your physical RAM, all of your frames, are already completely full with other pages. What on earth does the OS do now? It has to pick a victim. It has no choice. It has to choose a page that's currently in RAM and evict it, kick it out to the hard disk to make room for the new page it needs. And the algorithm it uses to make that choice has a huge impact on performance, because remember, going to the hard disk is incredibly slow. So let's compare two famous algorithms using this reference string here. It's just a list of pages our program asks for in order. First in, first out is the simple one. It just kicks out the page that's been in memory the longest, the oldest one. Least recently used is smarter. It kicks out the page that hasn't been touched in the longest time, basically guessing it probably won't be needed again anytime soon. And the way we measure performance is by counting page faults. That's every single time the OS has to stop and go get data from the slow hard disk. For this exact string of requests, the simple FIFO algorithm caused 6 page faults. But the smarter LRU algorithm, it only caused 4. The difference is intelligence. For example, they both see that page 2 is being asked for over and over. FIFO doesn't care. If page 2 happens to be the oldest, it's out. LRU, however, sees that page 2 was just used and correctly predicts it's probably going to be needed again soon, so it keeps it around. That better prediction led to 33% fewer slow trips to the disk. So from making one CPU feel like many to making a little bit of RAM feel absolutely enormous, the operating system is really the master illusionist of the entire computing world. It's this constant, high-stakes balancing act between speed, fairness, and efficiency. And that leaves us with one final thought. As our demands grow for things like instant AI and massive data processing, what fundamental limitation will the next great illusion in computing have to solve? Thanks for watching.